So, good afternoon. My name is Jim Gilson, and I'm going to be talking about network reliability monitoring for industrial control systems, so ICS SCADA. And this is really going beyond what NSM and SIEM can do into areas that they don't really work out so well. So, a little bit about me. I'm a senior investigator at Connexus Consulting. We're a small consulting firm that does reliability systems for industrial controls and SCADA. So a large portion of our business does safety systems, so fire and gas and safety and process hazard analysis, things like that. I work on the ICS networking and security side. So we do network assessments, security assessments, designs, things like that. And I'm also in the process of developing some software to actually automate some of what's in here. So I will not mention my product anymore, but basically we're doing this kind of stuff as we go along. Previously, I was in the NIST engineering lab for 20 plus years, doing cybersecurity and network performance for ICS systems. I've also worked in control systems, automated vehicles, wireless sensors and systems, things like that. For those that know anything about the ICS cybersecurity space, I'm the co-chair of the ISA 99 committee, which develops the 62443 series, and I'm also developing the security program for ICS SCADA as well. So what is network security monitoring? So NSM is, I'll read this, this is the collection, analysis, and escalation of indications and warnings to detect and respond to intrusions. And it's a way to find intruders on your network and do something about them before they damage your enterprise. So it uses a lot of the existing information that you have on your systems, so syslog and a lot of the different logging capabilities and tracking capabilities that you have on your network already, to monitor for things large scale over your whole system. Now, a lot of times it involves adding sensors to your system. So you've got to add sensors around your networks. A lot of times they're at the points that cross over zones. So they try and take all that kind of stuff, aggregate it into one location, and then look for security incidents. Now, what's SIEM? SIEM is something, it's sort of similar, but it uses a little bit different technology. And so SIEM products are available for real-time analysis of security alerts generated by network hardware and applications. So they do data aggregation, correlation, alerting, dashboards, a lot of similar kinds of things, but they use different technology. A lot of times SIEM systems are a dedicated product. And SIEM fits into a larger scale NSM system, but SIEM systems are something generally as a product you buy from a company that does these things. So this is not a talk about NSM and SIEM. I am not an NSM expert. I'm not a SIEM expert. I know a lot about the lower level protocols down in the ICS space. If you want to find out more about NSM, there's a Richard, and I've always messed up his name, Balich, I think. He's got some really good books on NSM. And then one of the other guys in the ICS space, Chris Sistrunk, he's got some really good presentations. He did the one at DEF CON this past year on NSM for ICS systems. And then, of course, you can pick your own search engine and find all sorts of stuff out on the internet. As always, take it with a grain of salt. Especially if you're going to vendor sites, they're going to claim they have the end-all, be-all of everything. So, when NSM won't work? If you can't observe the traffic that you care about, NSM really won't work. And then node-to-node activity in your network, though, is largely unobserved at the network level. So, when you have a lot of systems that talk to each other, and they're not actually going up through the architecture and crossing over zone boundaries, you don't have a lot of visibility into what they can do and what security indications there are going on. So here's an example ICS SCADA network architecture. This is the upper level architecture, so this is dealing with a lot of the server communications. So we've got business level systems, and they talk down to systems in the DMZ, and then they talk down to the plant control servers. And generally, you've got most of the traffic crossing across the boundaries. So you've got the majority of traffic at the servers are doing information passing between the DMZ, and then the DMZ is doing information down into the plant servers, and vice versa. So you're getting lots of circular communication going through these zone boundary points where you can actually put NSM sensors and get a lot of information out of your system. So you can do a lot of security monitoring at that. You're not dealing with a lot of the ICS protocols at this point either. So you've got a lot of more common protocols being used. So you've got XML information, you've got OSI Pi databases, you've got different kind of higher level protocols that are more well known, and there's stuff that's been written to actually analyze those even in the IT space. And then you've got more common platforms. So you have normal server kind of hardware. It sits in a rack and it gets all the normal data server kind of systems, datacom centers. So you can install things on them. You can actually put software on these, whether they're Linux, whether they're PC based. Most in the industrial world, almost everything is Windows server based. It's rare that you will find things that are not Windows server based. But things like Active Directory are run on here. Things like SQL databases, and a lot of this kind of stuff that already exists and the IT world knows about, they can analyze in NSM systems and get a lot of information out of that. So as I said, most of the network traffic crosses common boundaries. You can actually observe it with your actual NSM sensors that you can put in line. You can put taps in there and actually pull things off. You're not dealing with as many ICS protocols, so there's more automated traffic analysis, so you don't have to do as much by hand. You don't have to have an engineer actually sitting there looking at it. You can get Splunk or whatever product you choose to use can do a lot of that analysis for you. And then you can actually get things that have security logs. So you can find, you can install agents on them. Maybe you can actually get access to SNMP information. You can do your sys logs. You can have a lot of that information already existing on your platforms, and you don't have to do anything special to get that out. You just have to poll it at particular frequencies. So now, what happens down at the lower level of industrial control systems? So in these kind of cases, you have a lot of communications that runs locally in these subnetworks that exist down here. So this controller is going to talk to some devices here on this field bus, and it's going to talk to this little HMI server, a human machine interface, and maybe that's a PC, or maybe it's some form of specialized panel PC or things like that. But almost all of that communication resides inside this switch and never leaves that switch. And a lot of times these are layer 2 switches as well, so you're not talking about really smart kind of devices. Same thing, sometimes you have, it's not uncommon to have radio links between remote sites. So this may be an actual point-to-point wireless dedicated link using directional antennas and everything like that, or it's not uncommon to have radio links, satellite links between remote facilities. Generally, you won't see them. It's not uncommon, but it's not really as common to see them using the public telephone system anymore. Most of the time, they're doing more higher bandwidth radio links than trying to go over the POTS network anymore. So, but the majority of all that traffic resides and stays in these small remote sensors. You may have, say, an engineering workstation that can talk to these over the network, but it isn't constantly communicating. This is when they need to make a change, they go out, communicate with that controller, and they do a particular task, and then they log off, because you don't want to leave that session up and running, especially if these are low bandwidth links that are running over radio or satellite, things like that. You may have environmental sensors that are in your system. So the EPA comes into certain facilities and they've got to monitor 24/7. So they've got their own set of sensors that have to go through, and a lot of times there has to be a very specialized link through VPNs and or like their own separate line that they even bring into the facility. Only a very small amount of information actually makes it up into the plant servers. So the majority of traffic doesn't even really leave this network zone at all. And a lot of it, I would say 80+%, only stays inside those local switches. So you're not really going to have access to a lot of that information. And you're also dealing with very dedicated ICS protocols. These are protocols that are designed to do controls at that level. So there's Ethernet IP, there's Modbus, there's Profinet, there's a whole list of different control protocols that are out there that use Ethernet as a physical media. And some of them use different various levels of the TCP stack. Some of them use the full TCP stack. Some of them have found that they wanted to do more determinism, so they've actually like eliminated portions. So some actually will reside right on top of 802.3. Some actually even get rid of the link layer in 802 and run right over the hardware layer of 802.1 or 802.3. So they get down into really trying to do sub-microsecond real-time communications with their systems. And then you're dealing with ICS-specific platforms. So these are small computers that are about the size, some of them are about the size of your phone, but they've got to run 24/7 for the next 5 to 10 years and never be shut down. Think about that for a second. How many times do you reboot your phone? So, as I said, the traffic generally doesn't flow through any of these actual NSM sensors. In a system, you would have to literally put an NSM sensor off of here, hanging off of here, hanging off of both sides of this radio link, hanging off of this plant network control, and this is just a small one. In a typical plant, you're going to have anywhere from 20 to 30 of these ice or segregated networks inside the plant control network. So, and that's a normal size facility that I deal with, which is considered actually medium-sized, small to medium when it comes to actual industrial control plants. When you deal with large-scale SCADA systems like water utilities, wastewater, power plant utilities, pipelines, things like that, then you're dealing with sometimes you're dealing with like 1,000 independent, like isolated networks because you've got that many substations in your network or whatever. So. And each substation gets its own separate segmented network so that it doesn't transmit over back to the main network. So, yeah.
Quick question, do these switches communicate with each other? Like, if one switch went down, you tell me that whole subnet would go down, or, oh yeah. Wow, so they don't do Spanish or anything like that?
Yeah, typically these, and so typically these are not even, oh yeah. So yeah, the question was about basically load balancing on the switches and having like spanning tree running, and if these switches go down, what would happen if for that subnet going down? In reality, most of the time, unless these are truly critical systems, there's one switch, and that's it. You may have dual fiber coming in. So in some of the high availability systems, they will be dual fiber coming in to that switch. So they have two independent paths coming there. But that one switch, if that fails, you're done. So, but again, for critical systems, yes, you can actually have two switches and meshed and things like that, but you're most of the time talking about only two lines coming into there because in some of these facilities, like in a nuclear power plant, it's $5,000 a foot to run wire, minimum, and that it can go up from there. In like remote oil and gas pump fields, you've got fields that cover in like 25 square miles. So you're not going to be running wired communications to a lot of those So it's really difficult. You can run it to maybe like a centralized control center, and then you can plan for having dual path and redundant systems. And yes, in those kind of cases, like you will see a lot of times having independent paths so that when the forklift runs over or pulls down the fiber that's hanging on the poles, he doesn't shut down the whole plant. You've got another path over there, and redundant switches on both sides. But that's very rare. That's only for critical sites typically. The problem is you got to remember most of these systems have to actually sit in place for decades. I just got through a plant last year that had DEC alphas and running X11 traffic over their network, which is back mid-'80s. And they had a plan to replace it by 2018. These systems are older than you are. And they have to stay up and running 24/7, 365. So basically you have to deal with what exists. Because also, like, you can't get parts for a DEC alpha anymore. It's not, like, they went and actually, like, had to go and get someone to actually build replacement parts for them, especially because they couldn't get them anymore. Things like that happen, and that's not uncommon. That one was a more extreme example because they were just really, really bad. But it's not uncommon to see things in service for 15 years. So.
Another network. Couldn't you just set up one VLAN trunk on all those switches and then send all log traffic through it, and then you can monitor it all instead of setting up individual sensors? Just have one or multiple main sensors, load balancing across.
So the question was, couldn't you set up load balancing VLANs and things like that? In the way it's typically set up, the way we typically do, each one of these is a separate VLAN for performance reasons. No, it's specifically for performance reasons because these systems have to stay up and running, and they have to run continuously all the time, and determinism is much more important than security. So they would much rather deal with the VLAN stuff, and yeah, you can do trunking, and yeah, you can do monitor things and stuff like that, but also you're dealing with, a lot of times these are layer 2 switches. So they're not smart enough to do any of the VLAN trunking that you can do up at layer 3 routing kind of layer switches. So.
Is there anything you can do at those levels? Is that what the mitigation?
We actually have concentrated on assuming the hosts cannot be touched. So, so we have gotten to the point, I'll talk about it a little bit later, but basically we actually go in, and as long as these have mirror ports, we can basically go in and do assessments periodically and actually do signature-based detection. But it's developing a signature of what good looks like, and then comparing that signature over time. So that actually leads into some of the other stuff. So again, you're not dealing with standard OSs. A lot of time these are real-time OSs. If you've heard of VxWorks, that's a high-end one for a lot of systems, and so that's actually really good. A lot of these guys actually decide to write their own real-time operating systems because they can actually get down to sub-microsecond timings and determinism on a lot of these things. Sometimes down into nanoseconds of timing determinism kind of jitter on their communications. So very low determinism on their systems. So again, and then also, even when you have standard OSs in your systems, you can't always trust that the vendor will allow you to install something on there because they've got it sort of locked down as a warranty thing of, we won't service this if you install antivirus on it. because antivirus slows it down to the point where you've lost your determinism. So, as I said, the devices really aren't capable. A lot of times the information doesn't exist. And then the hardware designs, they're minimalistic designs. So, as I said, assume a cell phone from 10 years ago is what you're actually powering the substation on. That's the power you're dealing with typically. So what do? Looking at NSM a lot of times looks for negative cases. It looks for something bad happened, so I'm going to send an alert and someone should go and look at it. Well, in an industrial plant, looking at the negative is not always the best thing. What you want to do is actually look for the positive. Look for what it should look like, and then anything outside of that is actually what you want to look for. So looking for anomalies. Developing a known good set of traffic. I have not walked into a plant yet that everyone or like anyone knew what their traffic looked like on the network. They knew what it should kind of look like, but they never had done full traffic captures and actually gotten to the point of isolating each one of the traffic streams and looking to see what it should look like. And so these systems generally go through multiple levels of testing before they're actually up and running. There's usually some sort of factory acceptance testing of the systems before they even get to the site. Then there's site acceptance testing. Before there's actually like startup, a lot of times there's some sort of commissioning testing of the whole system. Then there's when you got your system changes, when any like major system changes, a lot of times they will have to go through and recertify it. And then almost always there's some form of periodic testing. A lot of times it's yearly. Sometimes it may be like 3 years or 5 years, but again, you're dealing with, there is some form of periodic testing that goes on these systems. And so what you can start to do is compare what the traffic looks like now to what it looked like during those known good sets. And if you see things that are out of the norm, if you see new traffic streams that shouldn't be there, if you see traffic streams behaving differently than they should, if you see anomalies in the traffic that are appearing that you didn't see before, that's something to alert. These systems don't change all the time. You don't have, you shouldn't have people down on the control networks looking at web pages. They shouldn't be going out to name your malicious actor country. They shouldn't go out to those countries. If you start seeing traffic going there, there's probably something wrong. Egress filtering for firewalls is one of the biggest things that should throw up red flags. If you start seeing egress traffic out of your company from the industrial control system directly, then you should be like running to figure out what's going on. Network reliability monitoring really doesn't have to be difficult. A lot of the tools exist already. I mean, I live in Wireshark and XML-like text files, or basically Excel spreadsheets. You can do a lot of what you need to do with Wireshark, and Wireshark will export PSML or PDML files, which are their packet data markup language. You can actually like look at the individual fields from there, and then you can process that pretty easily inside either Microsoft Excel or a lot of different tools and get some data out of there. I won't say it's the best data, but it's at least something to look at. And the metrics you're looking at aren't very difficult either. So you're looking at jitter on a deterministic signal. You should be getting a straight line across there, and all of a sudden I have some wiggle in there. Why? And so you go investigate that. And then latency. These systems, as a controller, I talk to some device, and that device responds back. How long does that latency take? What's the latency there? Almost invariably, it's the latency in the actual devices. If you're having network latency problems, then you need to talk to your ISP or you need to go to your network guys, but almost all the time, 95+% of the time, it's the devices that are actually having the problems. Unless you're dealing with manufacturing, and then it's usually the guys with the forklifts that run over network cables or do things like that. As I said, Wireshark really has a lot of capabilities. You're not going to find things like, I don't know if there was a Wireshark class here before, but basically like the TCP streams, you're not going to be able to use those really to follow industrial control system traffic. Generally, Wireshark doesn't know how to follow those TCP streams very well. What you need to do is actually get in and just learn how to do your filters really well in Wireshark, and you can filter down to getting all the individual streams.
Couldn't you write your own decoder for that?
Yes, you can. Yeah, so you can write your own decoder. What I personally do is I actually script T-Shark and use that as a way to do my filtering, because I can actually automate the process of scripting the T-Shark and then getting my data and then automatically pumping that into something else. So, but yeah, in Wireshark you can do that graphically or whatever. As I said, my company is developing a process to automate this. But I'm telling you that what I'm doing to automate the process is no different than what you can hand do with Wireshark and Excel. It's faster, it's cheaper, it's easier. So my company actually is doing it because when we go in and do assessments, I want to be able to go in, and I don't want to have to be the one to go to every single facility to look at the graphs and say, yep, that's good, or nope, there's something weird here. I want to send a junior guy out there to do the basic stuff, and maybe if he finds something really weird, he'll send me that, but I don't want to have to be the one to go out there to do it. Plus, we want to be able to actually teach end users how to do this stuff so that when they find the really bad stuff, they can come ask us, but we want to be able to sell them products and services associated with that. So really, it's really not that hard to generate basic graphs and charts. Now, as I said, detailed analysis of these things can take a lot more experience. I have been doing ICS network performance now for 15 or more years. I've seen enough graphs to kind of get a feel for what might be going wrong in some of these devices. And what we're trying to do is actually build some of that intelligence into our analysis tool so that it gets easier for end users to actually use. And then root cause analysis is one of those really hard things to do with this, because then the vendors actually have to get involved in a lot of cases if you've got devices that are showing weird things even like right from the factory. And I've done some prototype testing on vendor devices, and they have to then go back and sort of analyze all that traffic data and figure out, oh, it was something weird going on. Okay, so what do I actually look like? So this is a graph of what's called measured packet interval, and you'll see this nice sort of clear line at around 10 milliseconds. What you're actually seeing is the deterministic frequency of every 10 milliseconds this device was transmitting a packet on the network, and it should happen at approximately 10 milliseconds. These variations in here are the sort of like, it's sort of around 10 milliseconds, and as long as you're within a certain percentage, you can consider it a good device. In this particular case, you had 10 milliseconds and a 400 microsecond jitter, so that's a well-performing device. That's considered something that I don't have to worry about. This is another device, similar 10 millisecond, but it was slightly shifted off and it had a wider distribution. So if I did standard deviation and all the kind of math to go along with that, it would be a wider distribution here. But again, 10 milliseconds, 40 microsecond jitter, not that bad. So now you get some weird stuff happening. So this is actually a time scale. I've blown it up here so it actually shows up nice here on PowerPoint. But this is about a 60-second performance test that I was running. And you'll see there's actually some sort of beat pattern that happens every 30 seconds in this case. It's interesting. Again, this was one of these prototype devices where I had to like give it to the vendor and say, we saw something interesting, go figure it out in your system. I believe in this case it was actually a garbage collection routine they had running in their real-time operating system. They weren't using a standard one, they had written their own, and their garbage collection would go and actually slow down their communications. Is this a good, when we did the root cause analysis, we found the vendor was actually causing this problem. If I saw this in an ICS plant itself, would I know whether that's good or bad? If you've done the signature analysis, or at least signature collection earlier in your process, factory acceptance testing, SAT, commissioning, things like that, you would know that this device looks like this, and if I see this down the road, it's nothing special. So this is where you get into the, okay, what does it really look like? Not what it should look like, but this is actually what it really looks like. Another thing here too, here's another one. This actually had a beat pattern that was about 50 seconds long in this case, but again, lots of sort of wiggle traffic around there, and if I looked at this at an ICS plant, I would question them, well, what's going on to cause this? I would have to go back and actually dig deep into that vendor device to find out if that vendor device was the cause or if it was some sort of network attack or things like that. So a lot of these are more individual testing. I said, so what's causing some of these? So it may be garbage collection. Antivirus checks and updates are like terrible. Human-machine interface, HMIs, they will actually kind of like lock up when antivirus kicks in. Some AV vendors are worse than others at it too. The large-scale AV vendors are better, but even then they get kind of really hard on the system once they actually kick in. And again, you're dealing with systems that are process limited to begin with, and now you're loading it down with something that has to go out and download a 3 meg file every whatever, and oh, I've got to run my process and check to make sure everything's going wrong, but the nuclear power plant can't shut down right now because I've got to actually hit the button on the screen and make it do something. On-screen operations are actually another one of those that causes weird things to happen. Sometimes, especially Windows, will just go off into la-la land while it's waiting for some process to happen on the screen. You click the button and it kind of just decides not to react. So that's another reason why a lot of times the vendors will not allow you to install things on there that they don't know about because it could interfere with their HMI software or their whatever software they've got. And then you run into problems of, okay, well now who do I sue? And effectively that's what you're talking about in this case. The end user couldn't do something, they had a fault, they had an incident, who do they sue to blame for that incident going on? There's network anomalies. A lot of times in these plants, you've got large-scale EMI kind of interference. Large motors about the size of this room generating a lot of EMI interference, or welders, or toxic chemical areas where it actually corrodes the contacts and things. I was in a corn processing plant where the corn dust was actually eating away at the gold contacts on the RJ45 plugs. So they had to replace their switches every 6 months to a year because they were actually getting eaten away until they figured out, oh yeah, well, let's put some positive pressure, environmentally sealed cases in here and then work with those. But that was only in critical locations, not every location. Signal degradation, you're dealing with places where there's a lot of metal. Almost every machine is made of metal, and if you're actually dealing with wireless networking or something like that, you've got a lot of refraction, there's a lot of reflections you'll get, and you'll end up with a real mess in some cases. So they have to be really careful. Literally, like you could be here and get 10 reflections, and then here and you'd be fine. So it happens a lot. Flaky connections, stupid human tricks with forklifts and dump trucks and people hauling stuff around. You'll find anything that could go wrong with a network has happened in an industrial plant. And then maybe it is a security related incident. And then what happens? What do you do? So I actually decided to test this and see what happens when you actually run a man-in-the-middle attack against an industrial control system. I didn't bring it in here, but I have a little suitcase with a controller and an I/O block and some buttons. And it literally is just it's a switch. It's the Netgear like GS 108. So it's got a mirror port on it and 8 ports, so I can run that. I've got a PLC controller. It's a programmable logic controller. A 24-volt I/O block, and then what I did is I hooked up a Kali VM and Wireshark on 2 separate machines. So the Wireshark was on the mirror port and Kali was on the network. I am not a man-in-the-middle attack specialist. There's other people if you want to know. I'm a script kiddie, so I said ettercap. And so I ran the first one, which is ARP poisoning, and found some really weird stuff happened. I captured traffic on the mirror port. I was using a protocol called Ethernet IP. This is not Ethernet IP that we know. This is Ethernet Industrial Protocol. This is a trademark name, very bad name, but it is what it is. And running at 10 millisecond frequency. And I was running the man-in-the-middle attack against the controller itself. So I was actually trying to mess with the commands coming from the controller to the I/O block itself. So this is the communication actually from the I/O block back to the controller. And again, this was, I think this is baseline, but again, the I/O block didn't notice that the man-in-the-middle attack was going on for the entire time I was running. Didn't have any problems. Now, this is when I actually ran the man-in-the-middle attack against the PLC controller itself. So again, I have this nice, relatively stable connection at 10 milliseconds, and then this is where I ran the man-in-the-middle attack. And if you see, there's something happened there. Well, what happened? This is actually, the PLC itself did not even know that the attack was going on. It was too stupid to know. It just said, I'm sending my data, I'm sending my data. It never even knew that the man-in-the-middle attack was going. And this is likely due to the fact that this protocol actually uses a multicast signal for this. This guy actually transmits over multicast back to the controller. And that's actually it's actually for performance reasons, because this guy could actually be talking to a controller, could be talking to an HMI, could be talking to a historian, and you don't want to send 3 individual packets out there. You want to send one from this I/O block and have everyone just listen in on that, just like you would for video conferencing or things like that. So the protocol is designed to actually transmit multicast out. This guy listens to it, and because this guy continued to transmit over multicast, he had already set up and said, I'm going to listen to your multicast. He didn't even know anything happened with the man-in-the-middle attack. So with this, there actually was, I think, 3 additional packets in here because of the way I had the VM set up. I don't think I set it up properly, but there was, yeah. So there was a couple different streams of extra traffic in here, and I've actually signed up for Delaware to talk more in depth about this whole man-in-the-middle attack. So if you're in the area, I'm going to try and talk at BSides Delaware about that. And then when I actually isolated the PLC traffic from the man-in-the-middle attack itself in Wireshark, I was able to go and strip down into just looking at the PLC traffic itself. It didn't notice anything even happened. It didn't blip. Nothing happened at all. It was a nice straight line across the whole thing. And then what I did from there is I actually wrote some ettercap scripts to change the actual command signals to the PLC, or to the I/O block. So when it actually went and was trying to turn these lights on and off, I basically switched it to the other light. So you'd push the green one and the red button would light up, things like that. So, and I did this all in the man-in-the-middle attack. Again, the PLC didn't even notice anything was going on. There's a sequence number in the traffic stream to actually go and basically identify the packets, so that if you get one that's out of, because it's multicast, it's not using TCP, it's using UDP. So again, you don't have that session information to actually make sure you've got your session coming in the right order. So that's actually handled by the industrial protocol, and the industrial protocol can be spoofed by basically just advancing the sequence number out of range. So you can actually get it to basically forget about what's going on. And I just to try it out and see what happened, I actually ran my capture files through VirusTotal, Network Miner, and Bro. Oh, cool, thank you. So yeah, I did bring it with me, I just didn't bring it in the room. So I ran it through VirusTotal. VirusTotal noticed the ICMP ping messages, but it didn't actually trigger on an alert. Network Miner and Bro both did not trigger on an alert either when I was doing that. I didn't run ARP Watch against this, but I'm not sure what that would have shown. I just didn't have enough time to actually run it before I came here.
You were using a UDP-based code or something, I don't think they would hack something.
Well, it's an issue to deal with that it didn't even notice the ARP, the re-ARPing of the system and all. So NSM's good. If you're doing it, great. It doesn't cover everything though. And especially when you're down at the lower levels of ICS SCADA networking, it can be difficult to deal with. And then there are relatively easy ways to measure network reliability for industrial control systems. The tools exist, they're freely available. And as I said, there are some people that are actually trying to do some investigation down at the lower level. So that's my information. Yes? The question was, have we actually found anything malicious in industrial control system that we've gone in and done assessments? Yes. We've found active malware on some systems, and then we also found things that alerted as active malware, but were actually false positives too. We found actually, you'll find a lot more false positives than you will active malware, but we have found active malware on systems, and a lot of times it's where they did not protect or they didn't prevent the operators from loading web pages and plugging in their devices into the operator stations. So if they didn't have their firewall locked down to not allow web traffic through, then what happens a lot of times is they will introduce stuff by visiting whatever they go to. And it's sad to say, but it's not uncommon to see porn on HMIs in industrial control systems or other weird places that people have visited. So. It is actually on. We haven't noticed like malware down at that lower level, but we've noticed strange things happening. Let's just put it that way. Some of the industrial controllers have USB ports on them, and when the operator has to sit in front of that system for 20 or like 8 hours a day, and they want to charge their cell phone, but they haven't been told not to plug that into the HMI or into the controller itself, they will do stupid human tricks. And you will sometimes see weird things happening to the network. At that point, a lot of times it's easier to actually just reflash it than it is to try and fix whatever's going on. So if they start seeing weird things happening with the network, they will actually most times just re-upload the latest firmware of that device and the latest program, and that's it. So. It's rare that you will see ICS forensics down at the controller and lower levels. For the HMIs and PC-based systems, yes. But you're not going to see the FBI knocking on your door and saying, "Let me see your PLC." They just don't know what to do with that. Another thing too is that PLC has to stay powered in order to get the forensics off of it properly, and there isn't a really good way to do memory mapping on devices that don't have standard memory and standard interfaces. So you can't do a lot of that. As it is, the firmware for these devices is getting loaded into NVRAM anyway, so they'll just like reflash with what the vendor gave them to begin with and be done with it. So IR is not, they don't do a lot of IR and forensics in the ICS space simply because the devices just don't have that capability. So the question was about targeted threats. Do they consider themselves to be targeted threats? Some do. So I know Anonymous has Op Oil, and they've got some of those kind of things where they will attack, they will actively go after those kind of companies. And there's always pick your malicious actor country, and you'll see all sorts of warnings from ICS CERT and DHS and oh my God, cybers, and they're coming to get us. There's been a lot of that talk. Outside of Stuxnet, which was perpetrated by certain countries that we happen to maybe reside in, there aren't too many of those going on. You'll hear a lot of stuff, and you'll hear a lot of FUD about everyone's coming to get us, and this country and other countries are coming, and ISIS is coming, and everyone's coming to get us. There is some truth to that. They did find controllers in, they found like manuals for controllers. They found actual hardware in Afghanistan when they like did the whole bombing of that mountain. They found stuff in there. They found stuff when they've gone in to investigate a lot of things. You can get a lot of stuff on eBay. I mean, it's not that hard to get. And it's the same equipment for decades. So if you find something in there, it's not uncommon to find that same vulnerability in there for years. Again, it doesn't benefit the vendors in a lot of cases in these things to actually go out there and try and fix problems too. It's not like the vendor shaming that happens in the IT world. A lot of this stuff actually gets hidden behind closed doors because it does affect real things. And there is a real boom factor and big clouds of ethyl methyl death and stuff like that. So that stuff a lot of times is actually held closer to the chest by these companies because they don't want to release it out. So, any more questions? Thank you very much.